Welcome back to the IMSA workshop. And the first speaker of today's session is Professor Andrew Harder from the Lehigh University. And the title of the talk is Log Symplectic Pairs and Mixed Structures.
No, thank you very much for the introduction and for the invitation thank you to the organizers for the invitation to speak. And thank you to all of you for coming, early on a Friday morning, I guess. So as Tokyo said, I'm going to talk about log symplectic pairs and mixed Hodge structures. So, the basic plan for the talk is to start off by talking about K3s and their degenerations. This is sort of an old story. I'll talk about the corresponding Hodge theory and the geometry of the singular fibers. Then we'll talk a little bit about the resulting structures, so the log Calabi Yau surface pairs that arise from these degenerations as components of degenerations. I'll talk about their classification, their Hodge theory, and the relationship that these two different things have to the classification of degenerations of K3 surfaces. Then I'm going to talk a little bit about generalizations of both parts of the two previous bullet points to higher dimensions. So I'll talk about generalizing K3 surface degenerations to degenerations of holomorphic symplectic or hyperkaehler varieties. I'll talk about the corresponding limit mixed Hodge structures and things like that. So that's stuff that other people have done. Then I'll introduce the analog or sort of the corresponding analog of log Calabi Yau surface pairs, which I'll call log symplectic pairs of pure weight. I'll talk about some examples of these things, their cohomology, and how they relate to degenerations of hyperkaehler manifolds. Okay, so that's the basic idea for the talk. Right, so I can get started, I suppose. So I assume that everyone here has seen this, before, so I'll go fairly quickly over this part. So for me, I'm going to talk about semi-stable degenerations, and this is going to be a proper flat surjective morphism from some analytic space or analytic. This will be a manifold, so complex manifold X to delta, the unit disk, whose fibers away from zero are smooth, so that the fiber over zero is normal crossings. And I only have vanishing order 1 on each of the components of the fiber over 0, right? So basic things. So that's, I'm sure something people have seen. So these are, of course, well studied for curves and surfaces. They're, of course, more well studied for K3 surfaces than many other types of surfaces. And so for K3 surfaces, we have the following theorem. So this is a fairly old theorem of Kulikov, followed up by Person and Pinkham, which says that if I have a semi-stable degeneration whose smooth fibers are K3, and so that all the components of the central fiber are Kähler, right? So this is S0, and also so that the canonical bundle of the total space S is trivial, then there's three different types of, roughly speaking, three different types of degenerations that one can find. So there's type 1, which corresponds to smooth K3 surfaces. Type 2, so these are chains of surfaces which meet in smooth elliptic curves. So you have, on the endpoints, you have rational surfaces with smooth anticanonical elliptic curves. And in the middle, so you have a chain, and in the middle of these things, you have ruled surfaces over an elliptic curve, which are glued together along pairs of sections. So one section at each end. Okay. Right, so of course, basic examples of these type 2 degenerations are things like you take a quartic hypersurface in P3 and you degenerate to a union of a cubic and a plane. So this deformation, if you take the pencil of such surfaces, you're not going to get a smooth thing. You're going to have singularities. So once you resolve that in the appropriate way, you'll get a type 2 degeneration. Then there's type 3 degenerations. So this is degenerations whose central fibers are unions of rational surfaces, and the dual intersection complex of these surfaces is a triangulation of a two-sphere. So the most basic example of this is taking a quartic and degenerating to a tetrahedron of planes. Then you take the corresponding pencil or what have you of surfaces. This will have singularities. You then resolve, and you get a type 3 degeneration. So that's the Kulikov-Person-Pinkham classification. You can distinguish these three different types of degenerations via their Hodge theory. So specifically, if you think about the limit mixed Hodge structure associated to a degeneration, the, I guess, most important data when you talk about the weight filtration is the monodromy action, right? That's going to determine the weight filtration. So there's 3 different types of monodromy actions that you can have based on the different types of degenerations. So if your degeneration is of type 1, then your log of monodromy is 0. If it's a type 2 degeneration, then the log of monodromy has the property that n squared is equal to 0, but n is not equal to 0. And in type 3, sort of the what you'd expect is that the n cubed is 0, but n squared is not 0. So we can distinguish this way. And this gives the following types of limit mixed Hodge structures associated to these degenerations. So I'm drawing these funny little pictures here. And so the idea is basically with these pictures that if you have, so the rows or sort of correspond to the weight graded pieces and the columns correspond to the Hodge graded pieces of those weight graded pieces. So when I say this just means that this is purely in weight 2, and the cohomology looks like the cohomology of a K3 surface, corresponding to the fact that this is just a smooth K3 surface. In the type 2 case, you have this neat little splitting where you have an 18-dimensional piece right in the center, and then you have 2 pieces in weight 1 and 3, which look like the cohomology of an elliptic curve. And then you have the type 3 case where you have this Hodge-Tate type picture. So the only non-trivial weight-graded pieces are an even weight, and the corresponding Hodge-graded pieces are, of course, what you need to have, right? That has to add up in each column to 1, 20, and 1. Right, so this is how it works. Okay, so that's a fairly nice little story. If you have a degeneration of K3 surfaces, then the central fiber is composed, of course, of a bunch of different surfaces meeting in a normal crossings way by my definition of these things. So such a pair is called, when we take a degeneration of K3 surfaces, the pairs that we get this way are called log Calabi Yau. So it's a pair made up of a surface, one of the components, and its intersection with the other surfaces that make up the singular fiber. So this is going to be log Calabi Yau. So that means that the singular or the divisor that you get this way is simple normal crossings, and it's anti-canonical. So this is my definition of log Calabi Yau. Okay, so if you want to classify the log Calabi Yau surfaces or log Calabi Yau surface pairs, it again sort of falls into 3 different types. Type 1 is a smooth K3 surface, or maybe if you're being like more, maybe we don't need K3 here, maybe we can include abelian. In type 2, you have either one of the 2 following things, and this corresponds to the possible components in a type 2 degeneration. You have smooth rational surfaces with an anti-canonical elliptic curve, so like P2 and a smooth cubic. You can get a ruled surface over an elliptic curve with divisor composed of a pair of sections, right? So it starts with I'll mention a bit more about this in a second, but it starts with a split P1 bundle, and then you take the 2 sections. And then in type 3, you get rational surfaces with anti-canonical cycles of curves. Right? So this means that if you take the dual intersection complex of the collection of curves making up Y, each of these curves is going to be rational, and the dual intersection complex is just a cycle. So these are fairly easy to visualize. Okay, so not only do we have this rough classification here, we actually have a more precise classification of log Calabi Yau surface pairs in the sense that you can actually talk about where they come from. So smooth rational surfaces with anti-canonical cycle, or with smooth anti-canonical can be constructed from the following basic pairs. You take P2 with an elliptic curve, smooth elliptic curve, and F0 or F1 with a smooth elliptic curve, and you just take points inside of this elliptic curve and start blowing up. So that'll give you everything eventually. A similar construction tells you how to construct all of the second sort of subset of type 2 log Calabi Yau pairs. You start with a split P1 bundle over an elliptic curve. You take the 2 sections corresponding to the the splitting as a sum of line bundles, and you start to blow up points inside of those things, and you'll get any ruled surface over an elliptic curve that way. And in the third case, there's a similar construction again. You take any toric surface, x delta, so this is notation I'm using for toric surface, and you take the toric boundary, d delta, and you start by taking a whole bunch of smooth points in the boundary divisor, and you just blow these up in the same way as before. maybe multiple points at multiple times at the same point or something like this. But eventually you'll get all type 3 rational surfaces this way. Okay, so right, so that's the basic geometric classification here. We can also look at what the mixed Hodge structure on H2 of such pairs look like. So, I mean, the story is very similar to what you'd expect, or what we saw for degenerations. So I won't say anything about type 1 because it's just smooth, but type 2, you get sort of half of the picture that we saw for degenerations, corresponding to like some sort of Clement-Schmidt type thing. And then in the type 3 case, we again get sort of half of what we saw before. So we get a piece in weight 4 and a piece in weight 2 and nothing else. Okay, right. So that's my very quick rundown of what happens for K3 surfaces. If we go to higher dimensions, things become, of course, a bit more complicated, but there's still the same basic splitting of structures based on what happens in H2, right? So the idea for hyperkaehler varieties is always that the everything is sort of controlled by the symplectic form and things that happen in H2, or not everything, but largely speaking, this is where things come from. So you can, and this is at this point what I'm saying is a little bit artificial, but what I'm saying is that you can just split degenerations of hyperkaehler varieties up into 3 different categories based on how H2 degenerates, right? So there's type 1 where H2 doesn't really degenerate, where you have like basically a there's no real monodromy action. You have type 2 where it splits again in this way. So I have 1, 1 above and 1, 1 below. So elliptic curve pieces at the top and bottom. And then you have this Hodge take case, so the type 3. Okay, so I mean, does this actually give you anything geometric in the case of hyperkaehler varieties is sort of the question that you could ask. And Clara, Laza, Saka, and Voisin showed that really this does, give you some sort of geometric information, more than just saying this is what happens to H2. This tells you something about the geometry of the entire degeneration. So in type 1, after base change, you can make your degeneration smooth. And so, I mean, their assumption is weaker than what I was assuming before when I'm talking about semi-stable degenerations. They're just talking about DLT degenerations with this minimality condition. So DLT corresponds to my, well, I mean, it's of course a weakening of what I'm saying, simple numeral crossings, and minimality corresponds to the canonical bundle condition that I made, I think. Right, so in type 1, you can make it smooth after base change. And in types 2 and 3, you can get information about the dimension of the dual intersection complex of the central fiber. So in particular, in type 2, the dimension of the dual intersection complex is half the dimension, half the complex dimension of the smooth fibers. And in type 3, it's the dimension of or the complex dimension of the smooth fiber. Of course, there's more to it than this. I'm sort of giving a rough overview. There's more precise information. Okay, so that's the hyperkaehler, Hodge theory to degenerations geometry type picture. And if you want to talk about the cohomology of this, I think this is in some sense controlled by this conjecture of Nagai, or sort of this is what's expected is this conjecture here. And I'm going to paraphrase the conjecture just for my own purposes. But so what this conjecture says is that for a type 2 degeneration, then the weight graded pieces of these cohomology groups vanish for high enough weight, essentially. So there's a little bit more to it than this. I mean, I think part of this part of the conjecture also assumes that the 2jth piece doesn't vanish, but that's something that is, I think, proved by the same authors that I mentioned on the previous page. So, I mean, essentially, this is what the conjecture has been reduced to. And in type 2, or type 3, sorry, the conjecture is that the highest weight graded piece is just isomorphic to Q. Right? So it doesn't vanish, and so I mean, his conjecture was originally stated in terms of no potency order of the monodromy action on even cohomology, but this is sort of a Hodge theoretic. not restatement even, just like, I'm just saying this in a little bit of a different way. Okay, so that's conjecture. So the second statement was proved by Kolar, Lazasaka, and Voisin. And so the Tenkov proved something even stronger than that. So he proved that if you have a type 3 degeneration of hyperkaehler varieties, then the limit mixed Hodge structure is Hodge-Tate. So that is, I mean, if we go back to my pictures of cohomology or these mixed Hodge structures here, that basically means that the only non-trivial entries, if I were to draw this picture, are going to be on the diagonal. So it's like this type 3 case here. In terms of Deligne IPQs, this just means IPQ is non-zero only if P is equal to Q. Okay, so I mean, the way to interpret the statement, well, one way to interpret the statement is to say that being Hodge-Tate in H2 forces all the other cohomology groups to also have Hodge-Tate behavior. Right, so this is sort of in keeping with a lot of, things that we know about hyperkaehler varieties, which is that, what happens in H2 determines a lot of what happens in higher degrees. I should also make a couple of comments about the first part of this conjecture. So as I said, it was, partially proven by Kolar, Laza, Saka, and Voisin. But Green, Kim, Laza, and Robles have, I think, written down a proof a complete proof for all known examples of hyperkaehler varieties, right? So there's this relatively well understood list of known hyperkaehler varieties or manifolds. And for all of those cases, it's been checked that this conjecture holds. So, I mean, this conjecture is essentially settled if you believe, that those are all hyperkaehler manifolds. I mean, a slightly, I'll come back to this in a little bit. But what I'll talk about today, the techniques that are used here, I mean, I don't even know if this is worth mentioning really, but you can prove that this first part of Nagai's conjecture holds in dimension less than or equal to 8 for a special class of degenerations that are called good degenerations. So this may or may not be a new thing. Right. So it's sort of just this is not super deep. Okay, right. So that's so where are we? So this is I've sort of gone over what's known about the cohomology and degenerations of hyperkaehler varieties, and so I want to fill in the gaps. So in the next bit, so as I said before, or as I've sort of been trying to say. So there's this relationship between the geometry and Hodge theory of components of the degenerations of K3 surfaces and the way that the cohomology and geometry of the degenerations behave, right? So that if you look at the degeneration and you look at the components of the degeneration, you can compare the geometry of the degenerations, like the dimensions of dual intersection complexes and things like this. And the mixed Hodge theory of this degeneration, what is the structure of the cohomology ring, to the corresponding things about the components of this degenerate fiber. And then there's these nice relationships. And so we know a lot about, or a fair bit about, the situation for degenerations of hyperkaehler varieties, but the corresponding facts about the cohomology and geometry of the components of the degeneration are not quite so well known. So that's the idea now. So the idea is to fill in that gap, right? So to talk about the components of degenerations of hyperkaehler varieties and to study their cohomology and geometry a little bit. Right? So why would you want to do that? I mean, so first of all, I mean, I'm just curious. But second of all, I mean, if your long-term goal is to maybe construct new hyperkaehler manifolds by smoothing techniques or things like that, then one thing that you would like is to have a handle on what are the components of these degenerations, right? So this is maybe a very long-term goal, and I definitely put it with a question mark here. But Hanke has proved that if you have appropriate degenerate fibers, so things that look like the degenerate fibers of degenerations of hyperkaehler varieties, these can be smoothed. So a missing input, one of the missing inputs here, is to know something about the components of these singular fibers. So another reason that you might want to study these things is that they tend to appear when you study cluster varieties and things like that. So having a handle on their geometry might give us some insight into the structure of different types of cluster varieties and things along those lines. And so the cohomology rings, so why would you want to study structures of these cohomology rings? Well, I mean, for me, partially, it was mostly just curiosity. But one of the nice results that came out of this was that there were tools that sort of appeared that were, able to give some sense or some small results based on about Nagai's conjecture and things like this. So there was some feedback into the study of the cohomology of the limit mixed Hodge structures of degenerations of hyperkaehler varieties. So this is my sort of preamble part, motivation and things like that. Now I want to talk a little bit about actual results and things along those lines. Okay, so the objects that I want to study are called log symplectic pairs. So these are pairs that consist of a smooth variety of dimension 2D, so even dimensional things. And for me, it's going to be a simple normal crossings divisor. Okay, so it's going to be a pair, and it's going to have the we're going to have the existence of this log symplectic form here. So this is a log 2 form with logarithmic poles on the divisor y. So that if I take the dth power of this thing, this is now a non-vanishing section of this line bundle. So of course, this forces this bundle to be trivial, which forces your variety to be log Calabi Yau. So these are a special class of log Calabi Yau varieties, or log Calabi Yau pairs. So this is some sort of non-degeneracy condition. You can reinterpret this second part here as saying that if you think about this as a pairing or as a map between the tangent and cotangent bundle, or log tangent and log cotangent bundles of the varieties, you get an isomorphism. So it's essentially, a log version of the symplectic form condition that you would often see for holomorphic symplectic or hyperkaehler varieties. So what are some examples of this? In dimension 2, examples are fairly easy because this just coincides with being log Calabi Yau, especially under the SNC condition that I'm sort of placing here. So I mean, you of course don't need the SNC condition for this to make sense. You need a slightly more subtle definition of the log cotangent bundle, but that's about it. Right, if it's anti-canonical SNC, if your boundary divisor is empty, then this is just holomorphic symplectic. So of course, basic examples are Hilbert schemes of points on K3 surfaces, generalized Kummer varieties, the standard examples of holomorphic symplectic varieties. I'll give maybe more examples later. I mean, if I get time for it. But a less obvious example of these types of things is something that was constructed by Ran, which basically says that if you take a log Calabi Yau pair so that the boundary divisor is smooth, you can take the Hilbert scheme of points of that thing. So that thing's going to give rise to, it's going to be smooth itself, but the divisor corresponding to the chosen boundary divisor is not going to be SNC generally. It's going to have sort of slightly nasty singularities. If you take this as a pair without resolving singularities, it's log symplectic without the SNC condition. What Ron did was basically he proved that you can find a nice resolution of singularities, or you can blow up the boundary divisor so that it becomes SNC, essentially. So he gave, dimensions, examples in higher dimension of what I'm looking for here. So that's why I mentioned that. Okay, so those are, I mean, so hypothetically, these are the things that should appear as components and degenerations of hyperkaehler log holomorphic symplectic varieties. But, I'm placing very strong restrictions by saying SNC boundary. So I'll place correspondingly very strong restrictions on the types of degenerations that'll give rise to such things. So I'll study what are called good degenerations. So these are semi-stable degenerations, so that I have this relative log 2 form on my degeneration, so that it's this form is non-degenerate. So right, so if you look at this form and restrict to the smooth fibers, what you'll get is a holomorphic symplectic form. So the question they can sort of naturally ask is, what does it give you on the singular fibers of your degeneration, or the singular fiber of your degeneration? And the answer is relatively easy. So if you take an irreducible component of a good degeneration, so take one of the pieces of the singular fiber, take this thing, and take it as a pair with the intersection with all the other components of the degenerate fiber as your divisor, then the corresponding pair is log symplectic. So we get log symplectic things from degenerations of holomorphic symplectic things. And so this shouldn't really be surprising. I mean, this is essentially what happens if you take degenerations of Calabi Yau varieties, you get the same type of thing going on. So, you know, how do you prove this? I mean, proof is not so hard. You take d log pi. So pi is a map. You can take d log of that. This is going to be a log form. And then you take the wedge with the sigma. So wedging with sigma, or wedging with d log pi, moves you from being a relative log form, a relative log 2 form, to being a non-relative 3 form. Then you can just take the residue of that thing, and that'll give you your log symplectic form. Okay, so, and I should finish this slide with you know, my standard caveat that I am making a strong restriction by talking about good degenerations. So in dimension 2, many are known because it's dimension 2, and that's fairly easy. This is essentially the same thing as, you know, these Kulikov-Person-Pinkham degenerations. In dimension 4, Nagai has constructed a few of these things, or a class of these things, coming from Hilbert schemes of pairs of points on type 2 degenerations of K3s. But even that, you know, it's a fairly complicated construction. So, you know, this is very, you know, hypothetical. So I mean, these are things that are, you know, I don't expect too many of them to appear. So this is sort of just my idealized version of what's happening here. Okay, so right, so this is holomorphic symplectic. So holomorphic symplectic is bigger than hyperkaehler. So if I want to focus on hyperkaehler varieties, is there anything special that appears for these components? And the answer is, of course, yes. So I can take the Deligne decomposition of any mixed Hodge structure. So this is essentially your analog of the HPQ decomposition of a pure Hodge structure. And so I'm not going to spend much time going over this because either you know it or you don't, and you probably do. So let's see. So I'm going to place a restriction on holomorphic symplectic pairs based on this decomposition. So I'm going to say that if I take a log symplectic pair, this is composed of, you know, a variety and a divisor, but also a form, the log symplectic form. So I'm going to say that a log symplectic form has pure weight W. So this is, of course, going to determine an element in the de Rham cohomology. So if the corresponding element of the complement, so if the corresponding element lives in I2W, then I'll say that this is a log symplectic form of pure weight W. So by the construction of the Deligne decomposition, you know, the symplectic form, this lives in F2 on the first, you know, Hodge filtered piece, or the second Hodge filtered piece. So by definition, this symplectic form, it must live in the direct sum of I20, I21, and I22. So when I say pure weight, I mean it just lives in one of them. Okay, so, you know, of course, the thing that I'm leading up to is, how does this relate to degenerations of hyperkaehler varieties? So if I take a good degeneration, so that the smooth fibers of this degeneration are all themselves hyperkaehler, and if I take an irreducible component of this thing, and I take the divisor in this, you know, constructed in the same way as before, then what I can see is not only is that thing a log symplectic form, but it has this extra Hodge theoretic condition that the symplectic form is of pure weight. Okay, so there's a special nice element in its cohomology which lives in weight 4, or sorry, one of the specific weights in cohomology. Okay, Right. So of course you can. So maybe, I mean, I should make a note about how this is proved. You know, it's not very. It's not a super deep result. Basically, you want to show that the map that was given in the previous slide that tells you how to take a symplectic form on the degeneration to a symplectic form on a component, that this is coming from a morphism of mixed Hodge structures. And so you just prove that, you know, if I have a degeneration and I have a component of this degeneration, then there's this, you know, appropriate morphism of mixed Hodge structures. And, you know, for me, I was surprisingly unable to find this in the literature, but it was, I mean, it's not, you know, it's not rocket science. Okay, so you can, I mean, there's this correspondence between the weight of a degeneration and the type of a degeneration. So if I have a type 1 degeneration, this corresponds to weight 0. If you have a type 2 degeneration, this corresponds to weight 1, and type 3 corresponds to weight 2. Right, so see this fairly straightforwardly. Okay, so now, you know, I have, so this is my hypothetical, you know, characterization of the components of degenerations of hyperkaehler varieties. You know, just like in the case where we talk about log Calabi Yau varieties, not all log Calabi Yau varieties appear as components of degenerations, but this is, you know, one, you know, nice characterization of such things. Okay, so why should this be an appropriate analog of log Calabi Yau in higher dimensions? So in the sense that it sort of finishes, you know, the syllogism, you know, K3 surfaces are to log Calabi Yau varieties as hyperkaehler varieties are to, you know. Well, you can prove that a whole bunch of sort of structural results that we've seen already for degenerations of hyperkaehler varieties actually hold for such things. Okay, so you can prove a geometric result about the structure of the boundary divisor in these cases. So if you have a log symplectic pair with a log symplectic form of pure weight 0, then the boundary divisor is empty. So this corresponds to this base change result that if you have a type 1 degeneration of hyperkaehler varieties, then after base change, you get a trivial degeneration. In type, if you have a log symplectic form of pure weight 1, then you can check that the dimension of the dual intersection complex is, you know, essentially what you would expect. So half the dimension of the variety minus 1. And in weight 2, you can check the similar thing holds, you know, that the dimension of the dual intersection complex is the dimension of x minus 1. So these are things you can do. And so combined with the previous result, if you're allowing yourself to say semi-stable instead of DLT, which is a fairly strong condition, then this recovers, you know, the, I mean, I don't even maybe say, I don't know if recovers is even the right word. It's not really in the same ballpark, but it's a similar result. Okay, so I should also point out that this does, you know, say something relatively significant. You know, it says that just by looking at sort of obvious log symplectic pairs, you can find those which are not of pure weight. And therefore, you can find log symplectic pairs that don't appear as components of degenerations of hyperkaehler varieties. So for example, if you take a K3 surface, S1, and you take a pair consisting of a smooth rational surface S2 and a nodal anticanonical curve, so this is a cycle of rational curves, then you take the product of this thing as a pair, and what you get is log symplectic, but not, there's no symplectic form of pure weight. So such a thing can't appear as a component of a degeneration of a hyperkaehler variety. This you know, can likely be proven in other ways, but it comes from this for free. This also tells you that the characterization that I gave above in terms of, you know, what the dimension of the dual intersection complex of the boundary divisor is, this is not, you know, some sort of fundamental thing to pure weight. This is just sort of this consequence of pure weight. Okay, right. So that's, you know, my geometric discussion. So what I want to say now is a little bit about the cohomology rings of these types of things. So I'm going to split this up into 3 different sort of broad properties of cohomology rings. And I'm going to look at the pure weight 2 case and not the pure weight 1 case, just because it's a lot easier to talk about the pure weight 2 case. Pure weight 1, there's analogous results. Pure weight 2, it's a lot easier to say. So the first property, which is just a proposition really, is that if I have a log symplectic form with a symplectic form sigma, then the cup product with sigma induces isomorphisms in graded pieces and Hodge graded pieces on the mixed Hodge structure. Right, so so I take the correct Hodge graded pieces of HP plus Q and I get a map to H2D minus P plus Q. Right, so essentially, how should you interpret this? Well, the same way you would interpret sort of the corresponding result for hyperkaehler varieties, right? So, this is the consequence of the fact that sigma is a non-degenerate log form, log 2 form. Right? So, the idea is that if I draw this diamond representing the Hodge graded pieces in cohomology of a non-compact variety, so this will be, the dimension of H0. This will be the dimension of the first Hodge graded piece of H1. This is the dimension of the 0th Hodge graded piece of H1, and so on. So the same way I might draw a Hodge diamond of a smooth compact variety, I can draw a Hodge diamond associated to any variety. The same boundaries apply. But we'll, generally speaking, we'll lose the general symmetries, right? So there's no, vertical symmetry or horizontal symmetry if I take a non-compact variety, but I can still draw the same pictures. So what this symmetry statement is saying is that if I think about this Hodge diamond, then I get this diagonal symmetry across here. Okay, so that's the basic proposition. It's not so hard. Furthermore, you can say a bit more in the weight 2 case or the pure weight 2 case. So I said a little bit about this before, but maybe I'll give a proper definition. So I'll say that a mixed Hodge structure is Hodge-Tate if the odd weight graded pieces vanish and the weight and Hodge filtrations are opposed. So this is a statement about the relative dimensions of the weight graded pieces and the Hodge graded pieces. But I mean, maybe the most transparent way of saying this is just that the IPQ groups, these are trivial unless P is equal to Q. So you can state this also in terms of, the dimensions of the Hodge graded pieces of weight graded pieces, but it's most concisely stated in terms of IPQs. In terms of the pictures that I was drawing before, again, this just means that everything lives in the diagonal. Okay, so that's Hodge-Tate. Right, so this is, I actually made myself a little picture. So yeah, so it says that everything's sort of in this diagonal and everything off the diagonal is 0. So the theorem that you can prove is that if I have a log symplectic pair of pure weight 2, then the corresponding Hodge structure on the complement of Y is Hodge-Tate. So this places restrictions on the weights that can appear. So only, or the combination of weights and Hodge graded pieces that can appear. Okay, so so combining this with so yeah, I should bring this back to what I was saying before. This is the analogous statement to what Soldatenkov has proved about degenerations, so type 3 degenerations of K3 surfaces. So he proved, as I said, that the cohomology groups or the limit mixed Hodge structures are Hodge-Tate. So this statement here is that if you take the pieces of these degenerations, so if you take a good degeneration and you take the pieces of this degeneration, then the cohomology groups of those things themselves are Hodge-Tate. So the proof of this is completely different, of course. It's not the same as Soldatenkov's proof at all. This is just a fundamental thing about the behavior of a symplectic form. Okay, so combining the previous two results, essentially, and I'm not going to define this in great detail, but combining these two things, you get what's called the curious Hard-Lefschetz property for the cohomology rings of log symplectic pairs. And this is, as I said, just a consequence. Essentially, this is just the two previous results put together with a little bit more. But yeah, so this is just a statement about the behavior of this. So, I mean, essentially what this is saying is, well, I won't get too deep into it for, I guess, time reasons. Right, so this was the corollary. Okay. Lastly, the last thing that I should mention about the cohomology of log symplectic pairs of pure weight 2 is that these two things, or all these things put together, gives you vanishing results about the cohomology groups. So in particular, it says that HI is trivial if I is greater than 2D. So that means if I'm drawing these pictures as I was before of the Hodge numbers of, or the graded pieces, the Hodge graded pieces of the cohomology groups, then I have vanishing of these Hodge graded pieces above the dimension D. Right, so just, I guess this picture sort of summarizes the structure of, well, at least the Hodge graded pieces of the cohomology of a type of a log symplectic pair of pure weight 2. It says that the only non-trivial pieces in these cohomology groups can appear in this quadrant here. And then there's this symmetry across the diagonal. So it's very nice and compact. And sort of what this picture isn't showing is the fact that the cohomology is also Hodge-Tate. Okay, so that's this. And so I should just before moving on, I'll mention that the methods that I used to prove the results on the previous page, these are just based on, starting with the structure that is, some sort of graded ring so that each graded piece admits a mixed Hodge structure. And then there's the symplectic form like object that moves things along. You basically prove it from this general setup. There's not really much that's not, just formal in this proof. So all of these results have analogs for degenerations of hyperkaehler varieties or good degenerations in general. So you can prove the following types of things. So you can prove this theorem of Solda-Tenkov again in a slightly less general context. But if you say that if you have a good degeneration of type 3, then you can say that the limit mixed Hodge structure is Hodge-Tate. And you can generalize this a little bit too. So I mentioned this curious Hard-Lefschetz property before, and the statement that the cohomology groups of pure weight 2 log symplectic pairs have curious Hard-Lefschetz property in their cohomology. This transfers to an analogous statement about the cohomology of, the curious Hard-Lefschetz property for the cohomology groups of degenerations of type 3 of hyperkaehler varieties. And right, so you get this curious Hard-Lefschetz property, which is related to a P equals W type result that I proved with Li, Shen, and Yin, which I should also say is largely based on the work of Shen and Yin, not me that much. Okay, so you get this nice related result. And as I mentioned earlier, you get a result related to Nagai's conjecture. So it says that Nagai's conjecture is true for good type 2 degenerations in dimension less than or equal to 8. So unconditionally, this is just a statement about how Hodge structures work. And I should just, for the sake of completeness, I don't really think that this has much to do with the good degeneration structure. I think it just has to do with the behavior of the symplectic form in the limit. So I suspect that this part can be improved on beyond the good degeneration case, because as I said, that's a very strong restriction. Okay, so I've got about 5 or 10 minutes left. I'm going to sort of briefly take a look at collections of examples of these types of things. So yeah, as I said, there's these, this collection of structural results for log symplectic pairs. I mean, where do they apply? What can they do? So if I want to produce a log symplectic pair of pure weight 2, I've actually tried quite a bit to construct such things without much success. The only reliable method of construction I have starts with toric varieties and uses a sort of a cluster type construction, but it goes in sort of in the following way. So you start with the toric variety of dimension 2D. So this is determined by a fan inside of a lattice, as usual. I take the big torus inside of this toric variety, and I can choose coordinates inside of this big torus, and I can just define a holomorphic 2 form on the big torus in the following way. Or right, so this is so alpha ij. These are just a choice of numbers for I and j with this so that you get an actual 2 form this way. So then if you take this corresponding form, if the form determined by alpha ij, if this is a non-degenerate form, then the pair here is going to be log symplectic. So take the toric variety associated to the fan and take the toric boundary. Such a form in this like this is guaranteed to have log poles along the toric boundary, no matter which toric boundary you choose. And then if it's non-degenerate, it's log symplectic. So this is your most reliable construction of log symplectic pairs. Though from the perspective of, if I'm thinking about the cohomology of the complement, this doesn't really give me much. This just gives me the 2D dimensional torus, right? So this is not a very interesting construction from that point of view. But we get one, and I'll explain in a little bit how to get more. So before saying much more, I'll mention that you can get at least one fairly nice example of a log symplectic pair of type of pure weight 1 from a construction of, well, it starts with Fagan and Odesky. Then there's subsequent work of Gualtieri and Pym. And I guess there's even more work of Pym on this construction. So basically what you do is you take a smooth elliptic curve. You take an embedding of this thing into P4 of degree 5. Then you take its secant variety. So this is, of course, just the union of all lines passing through pairs of points inside of this thing. So the secant variety is a quintic hypersurface. It's very singular, though. It's got a singularity along a subvariety which is biregular to the symmetric square of the original elliptic curve. If you blow up this very singular divisor along the singular locus, that'll give you a SNC pair consisting of 2 different divisors. So one of the divisors is, of course, going to be the exceptional divisor, which is just a P1 bundle over the secant or the symmetric square. And then the other divisor is, just the resolution of the secant variety. So right, so the corresponding thing will give you a log symplectic pair of pure weight 1. So if you want to drop the SNC condition, then without this blow up process, you still get a log symplectic pair. But if you want SNC, you need to do this blow up. Okay, so that's the construction of Gualtieri and Pym. And so the idea is that from any log symplectic pair of pure weight, you can construct more if you know the symplectic leaves of this of the corresponding Poisson structure. So anytime you have a log symplectic form, you get a Poisson structure on X. And so I want to talk about symplectic leaves that live inside of the boundary divisors. So if I take a component y prime of y, so the y is the boundary divisor, take one component of this. This is foliated by symplectic leaves, and these are just places where the residue of sigma vanishes. So these are subvarieties on which the residue of sigma vanishes. And the theorem corresponding to this is basically that if I take these, if I take a nice enough symplectic leaf, so that is something that lives inside of a specific boundary divisor, and intersects the intersection of these, so the singular locus of the boundary divisor nice enough, then what I can do is I can blow up my original variety in a symplectic leaf, and I can take sort of a resulting variety. So I can take the proper transform of the original boundary divisor and the blow up, and this will provide for me a log symplectic pair of pure weight W. So, I mean, to some extent, this whole process is something that's at least implied in the literature. The new input into this is the fact that this preserves the pure weight condition. Okay, so that's the theorem. You can construct more. So once you have examples of log symplectic pairs, you can always construct more by blowing up symplectic leaves in the boundary divisors. Okay, so generally speaking, maybe the most interesting application of this is to symplectic leaves that come from the toric varieties that I was talking about on several slides ago. So if you take a toric variety, you have this log symplectic structure, assuming your toric varieties of even dimension. You can then detect what the symplectic leaves and the boundary divisors look like by essentially looking at the combinatorics of the structure. So, right, so as I said before, the log symplectic form omega is essentially a non-degenerate alternating pairing on the lattice M. So the underlying lattice M, maybe M tensor R technically, but if you take it to be integral, things are nicer. The toric boundary divisor, so if you pick a specific toric boundary divisor, so this corresponds to the Y prime that I was talking about on the previous slide. This corresponds to a ray in the fan. And for every ray in the fan, you can take a primitive element in that ray, and that'll give you just a primitive element in M. So therefore, you get two pieces of data from the symplectic form and boundary divisor. You get a pairing and you get an element in M. So you can combine this together to give you a map from M to Z. So that is an element in N. And that corresponds to a monomial function on the big torus. So, right, so that's how toric varieties work. So if I take the intersection of the closure of this thing as a function of the fibers of this map and the original boundary divisor, that'll give me a symplectic leaf. So there's this just combinatorial way of determining what the symplectic leaves of this Poisson structure are, or what some specialized class of these symplectic leaves look like. And so in this case, what we can do is we can do the same thing that we did before. We can choose the combinatorial data of a fan, and we can choose the data of a symplectic form, and we can just, under special conditions on the fan, so this is a sort of subtle thing, but what do you say about this fan and what do you say about this symplectic form for these leaves to intersect properly? That's sort of a good question. But if you do this in a careful enough way, you can specialize combinatorially how to build a nice collection of symplectic leaves in the boundary of a toric variety. So once you do that, you can blow up the symplectic leaves and you can construct families of log symplectic pairs of pure weight 2. And when you do this, what you get, so each of these blow-ups corresponds essentially to adding a cluster chart. So what you get are these, this slight generalization of, this family of cluster type varieties. And in particular, if you start with the case of where your adjacent alpha is the adjacency matrix of a acyclic quiver, and sigma is the standard simplex. So essentially you take Cn and you take, your symplectic form determined by the adjacency matrix of an acyclic quiver. This produces what are called acyclic cluster varieties. And so the consequence of this is that acyclic cluster varieties have these nice compactifications, which are log symplectic of pure weight 2. And applying the cohomological results, you can recover this result of Lam and Spire, which says that the cohomology rings of acyclic cluster varieties have the curious hard Lefschetz property. So you get another proof of that this way. Yeah, so I have a little bit more to say about the example of Plim and Gualtieri, but I think I'll end here, and that'll be it for me today.
Thank you for the talk. So is there any question? If not, thank you again for the speaker.